What if Earth's strangest monsters aren't on land, but hidden deep in the sea? Tonight, we'll meet Gulper eels with jaws bigger than their bodies, armored giant Isopods crawling the sea floor, and Siphonophores, one creature made of many. So before you get comfortable, take a moment to like and subscribe if you genuinely like what I do here. And let me know in the comments where you're tuning in from. Now dim the lights and let's ease into tonight's journey together. Deep beneath the waves, where sunlight has never touched, and pressure would crush any surface dweller in an instant, evolution has gone completely mad. The creatures that call these depths home don't just look alien, they challenge everything we thought we knew about what it means to be alive. They possess body plans so bizarre, so seemingly impossible, that if we encountered them on another planet, we'd assume they were the products of some extraterrestrial intelligence with a twisted sense of humor. But these monsters are real. They swim, hunt, reproduce, and thrive in ways that seem to mock the very foundations of biology. Their existence forces us to confront a humbling truth. Life doesn't care about our preconceptions. It doesn't follow our rules or conform to our expectations. In the crushing darkness of the deep ocean, evolution has written its most surreal poetry in flesh and bone. Consider for a moment the Gulper eel, a creature that appears to be nothing more than a living mouth attached to an impossibly thin tail. Its jaw can unhinge to reveal a cavernous maw that dwarfs its entire body, creating what looks like a nightmarish puppet operated by some malevolent force. Yet this isn't the product of supernatural horror. It's the result of millions of years of evolutionary refinement, each bizarre feature serving a purpose in the alien environment of the deep sea. Or take the giant isopod, a creature that looks like it crawled out of a science fiction film about armored aliens. These massive crustaceans, some reaching nearly 2 feet in length, lumber across the seafloor like living tanks, their segmented bodies protected by armor that would make a medieval knight envious. Their pillbugs scaled up to monstrous proportions, existing in a world where such gigantism shouldn't be possible. Then there are the Siphonophores, creatures that blur the very definition of what constitutes an individual organism. These aren't single animals, but colonies of specialized beings working together so seamlessly that they function as one entity. Some stretch longer than blue whales, creating ethereal, translucent curtains of death that drift through the water column like living galaxies. The deep ocean is Earth's last frontier, more alien and unexplored than the surface of Mars. We know more about the topology of the moon than we do about the deepest parts of our own planet. In this vast underwater wilderness, covering more than 60% of Earth's surface, creatures have evolved solutions to survival that seem to come from the fevered imagination of a cosmic horror writer rather than the measured processes of natural selection. But why are these creatures so strange? The answer lies in the extreme nature of their environment. The deep sea is a realm of perpetual darkness, crushing pressure, near freezing temperatures, and scarce food. In such conditions, conventional body plans become liabilities. The sleek, streamlined forms we associate with fish, the sturdy frameworks of land, mammals, the delicate structures of surface-dwelling organisms, all of these become not just useless, but actively harmful in the abyss. Pressure at depth isn't just intense, it's transformative. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater than at sea level. It's like having the weight of 50 jumbo jets pressing down on every square meter of your body. For most life forms, this would mean instant death. But the creatures of the deep don't just survive this pressure, they require it. Bring them to the surface and they literally fall apart, their bodies expanding and rupturing as the pressure that normally holds them together disappears. Food in the deep sea doesn't grow on trees or graze in meadows. It falls from above in a constant but sparse rain of organic matter, the remains of organisms that lived and died in the sunlit waters far overhead. This marine snow, as scientists call it, provides the foundation for all deep-sea life, but it's unpredictable and often insufficient. In response, deep-sea creatures have evolved to be opportunistic in ways that surface dwellers can barely comprehend. Some have developed mouths and stomachs that can expand to accommodate prey larger than themselves. Others have learned to go without food for months or even years at a time, their metabolisms slowing to barely detectable levels. Still others have abandoned hunting altogether, instead forming partnerships with bacteria that can create food from the chemicals seeping out of underwater volcanic vents. The darkness of the deep sea has also driven evolution in directions that seem almost magical. Bioluminescence, the ability to create light through chemical reactions, is so common in the deep ocean that it's more unusual to find creatures that don't glow. These living lights serve as lures, warnings, communication systems, and weapons. Some creatures create complex light shows that would make a fireworks display seem dim by comparison. Others use their bioluminescence like a burglar's flashlight, illuminating their prey just long enough to strike. Temperature in the deep sea hovers just above freezing, creating another challenge that has led to remarkable adaptations. Some deep-sea fish have antifreeze proteins in their blood that prevent ice crystals from forming. Others have metabolism so slow that they seem to exist in a state of suspended animation, moving through their world like living ghosts. But perhaps the most alien aspect of deep-sea life is how it challenges our understanding of what constitutes an individual organism. On the surface, the boundaries between creatures are usually clear-cut. A lion is a lion, a tree is a tree, and while they may interact with each other, they remain distinct entities. In the deep sea, these boundaries become fluid. Creatures form partnerships so intimate that they become single organisms. Parasites become so integrated with their hosts that removing them would kill both. Colonial animals create superorganisms that dwarf whales while being composed of thousands of tiny interconnected parts. These aren't just biological curiosities to be catalogued and filed away in some dusty museum. The strange body plans of deep-sea creatures represent solutions to problems that we're only beginning to understand. As we push the boundaries of technology, exploring space, and developing artificial intelligence, we're finding that the solutions nature has already developed in the deep ocean offer blueprints for innovations we haven't even dreamed of yet. The bioluminescent systems of deep-sea creatures are inspiring new approaches to lighting and display technology. The pressure-resistant structures of deep-sea animals are informing the design of submarines and deep-sea equipment. The colonial organization of Siphonophores offers insights into swarm robotics and distributed computing. The extreme longevity and slow metabolism of some deep-sea creatures might hold keys to understanding aging and developing life-extending treatments. But beyond their practical applications, these creatures serve as humbling reminders of how much we don't know about life on our own planet. Every deep-sea expedition brings back new species, new forms of organization, new ways of being alive that we never imagined possible. The deep ocean contains an estimated 80% of all life on Earth, yet we've explored less than 5% of it. We're surrounded by aliens, and we don't even know it. As we stand on the shore, looking out at the seemingly familiar surface of the ocean, it's easy to forget that beneath those waves lies a world more alien than anything science fiction has ever conjured. A world where evolution has thrown out the rulebook and written something entirely new. A world inhabited by monsters that shouldn't exist, but not only exist, they thrive. The creatures we're about to encounter in this journey into the abyss will challenge every assumption you have about what life can be. They will make you question the boundaries between individual and collective, between predator and prey, between possible and impossible. They are the products of evolution unleashed, unbound by the constraints that shape life in the sunlit world above. These are the monsters that shouldn't exist, but they do, and their existence makes our planet a far stranger and more wonderful place than we ever dared imagine. In the pitch-black waters 3,000 feet below the ocean's surface, something impossibly strange drifts through the void. At first glance, it appears to be nothing more than a disembodied mouth floating in space, a gaping, pink-lined cavern fringed with needle-sharp teeth. Only closer inspection reveals the thread-thin body trailing behind it like an afterthought, as if evolution forgot that mouths typically need bodies to support them. This is the Gulper eel, and it represents one of the most extreme examples of evolutionary specialization ever recorded. Its scientific name, Uropharynx pelicanoides, hints at its most shocking feature, that massive, pelican-like jaw that can unhinge to reveal a throat cavity larger than the rest of its body combined. But calling it an eel is somewhat misleading. While it belongs to the order Anguilliformes, which includes true eels, the Gulper eel has diverged so dramatically from its ancestors that it inhabits its own unique family, a testament to just how far evolution has pushed this creature away from conventional fish anatomy. The Gulper eel's body plan seems to violate basic principles of animal design. In most vertebrates, the head represents a small fraction of the total body mass, housing the brain, sensory organs, and feeding apparatus, while the body provides locomotion, energy storage, and reproductive capacity. The Gulper eel has inverted this relationship almost completely. Its head, dominated by that enormous mouth, can represent up to 25% of its total body length when fully opened. The mouth itself isn't just large, it's architecturally impossible by normal standards. When a Gulper eel encounters potential prey, its jaw doesn't simply open, it transforms. The lower jaw drops down and extends forward, while the skull actually flexes backward, creating a feeding cavity that would make a python jealous. The throat expands like a balloon, creating a chamber so large that the eel could theoretically swallow prey significantly larger than itself. This isn't just impressive, it's physically bewildering. The biomechanics required to create such a structure while maintaining the ability to swim, digest food, and perform other essential functions shouldn't work according to conventional understanding of vertebrate anatomy. The secret lies in the Gulper eel's revolutionary approach to skeletal structure. Where most fish have relatively rigid skulls designed to withstand the forces generated by powerful jaw muscles, the Gulper eel has evolved a skull that's more like a collapsible framework. The bones of its jaw and throat region are connected by highly flexible joints and expandable membranes. The hyoid apparatus, the set of bones that supports the tongue and throat in most vertebrates, has been radically modified into a system of struts and supports that can extend the feeding cavity far beyond what should be anatomically possible. But this incredible feeding apparatus comes with significant trade-offs. The Gulper eel's body behind the head is remarkably thin and delicate, more like a living ribbon than a typical fish. This thread-like body contains all the organs necessary for life: heart, liver, kidneys, reproductive organs, but they're compressed and arranged in ways that would be lethal for most other vertebrates. The eel's spine consists of more than 750 vertebrae, each one tiny and flexible, creating a structure more like a biological chain than a rigid backbone. This extreme body plan makes sense only in the context of the Gulper eel's environment and feeding strategy. In the deep ocean, food doesn't come in convenient, regularly sized packages. A gulper eel might encounter a small crustacean one day and a fish 3 times its own body diameter the next week. Traditional predators would have to pass up the larger meal, but the gulper eel has evolved to take advantage of whatever opportunity presents itself, regardless of size. The physics of deep-sea life also play a crucial role in making the gulper eel's body plan viable. In the crushing pressure of the deep ocean, the distinction between internal and external pressure becomes less relevant. The eel's body is essentially at the same pressure as the surrounding water, which means it doesn't need the rigid structural support that surface-dwelling animals require. This pressure equilibrium allows for the extreme flexibility that makes the gulper eel's feeding strategy possible. Digestion in the gulper eel is equally remarkable. After swallowing a large prey item, the eel's throat remains distended for days or even weeks as the meal is slowly broken down. The stomach can expand to enormous proportions, sometimes making the eel appear pregnant with its own food. During this period, the eel becomes less mobile, relying on the energy from its meal to sustain it through what might be a long period before the next feeding opportunity. The gulper eel's sensory systems have also adapted to support its unique lifestyle. Its eyes are tiny and likely of limited use in the absolute darkness of its habitat. Instead, it relies heavily on its lateral line system, a network of pressure-sensitive organs that can detect the movement of other organisms through the water. This system is so sensitive that it can distinguish between the swimming patterns of different types of prey, allowing the eel to assess whether a potential target is worth the considerable energy investment required to execute its dramatic feeding display. Bioluminescence plays a crucial role in the gulper eel's hunting strategy. At the tip of its whip-like tail is a small but powerful photophore, a light-producing organ that can generate bright flashes of bioluminescent light. This tail light serves as a lure, drawing curious prey within range of that enormous mouth. The eel can control the intensity, duration, and pattern of these flashes, creating complex light displays that mimic the bioluminescent signals of other deep-sea organisms. The reproductive biology of gulper eels remains largely mysterious, but what little we know suggests it's as extreme as every other aspect of their anatomy. Like many deep-sea eels, gulpers are thought to undergo dramatic transformations as they mature sexually. Their already enormous mouths may become even larger, while their digestive systems atrophy as they focus entirely on reproduction. Some researchers believe that gulper eels may only reproduce once in their lifetime before dying, a strategy known as semelparity that's common among creatures living in resource-limited environments. The distribution of gulper eels around the world's oceans reveals another aspect of their remarkable adaptation. They're found in every major ocean basin, from the Atlantic to the Pacific to the Indian Ocean, but only within a specific depth range, typically between 1,500 and 9,000 feet below the surface. This narrow bathymetric range represents the zone where their unique feeding strategy is most effective. Too shallow, and there are too many conventional predators competing for the same resources. Too deep, and even the sparse food resources of the midwater become insufficient to support their energy-intensive lifestyle. Recent advances in deep-sea observation technology have revealed new insights into gulper eel behavior that make them even more extraordinary. High-definition cameras deployed on remotely operated vehicles have captured footage of gulper eels using their enormous mouths not just for feeding, but for defense. When threatened by larger predators, a gulper eel can inflate its throat cavity to massive proportions, making itself appear much larger and more formidable than it actually is. This behavioral adaptation represents yet another innovative use of their remarkable anatomical specialization. The evolutionary history of the Gulper eel raises fascinating questions about the pathways that led to such an extreme body plan. Fossil evidence suggests that the ancestors of modern Gulper eels began developing in large jaw structures over 50 million years ago, during the Eocene epoch, when the deep ocean was undergoing significant environmental changes. The gradual cooling of ocean temperatures and the establishment of modern deep-water circulation patterns may have created the selective pressures that favored increasingly specialized feeding strategies. From a biomechanical perspective, the Gulper eel represents a masterclass in evolutionary engineering. Every aspect of its anatomy has been optimized for a single function, capturing and consuming prey of unpredictable size in an environment where such opportunities are rare and precious. The trade-offs required to achieve this specialization are enormous. Gulper eels are poor swimmers compared to other fish of similar size. They're vulnerable to predation when their throats are distended with food, and their entire life strategy is a high-risk, high-reward gamble on encountering large prey items. Yet this apparent vulnerability is also their greatest strength. In an environment where most predators are limited by the size of prey they can consume, Gulper eels have broken free from those constraints entirely. They've evolved to be opportunistic in the extreme, capable of taking advantage of feeding opportunities that would be impossible for any conventionally designed fish. The study of Gulper eels continues to yield insights that challenge our understanding of vertebrate anatomy and physiology. Their unique approach to skeletal structure is inspiring research into flexible robotics and expandable engineering structures. Their ability to rapidly change body shape and volume is informing studies of soft-bodied robotics and adaptive materials. Even their bioluminescent luring strategies are being investigated as models for new approaches to autonomous underwater vehicle design. But perhaps the most profound lesson of the Gulper eel is philosophical rather than practical. This creature represents life's ability to find solutions to problems we didn't even know existed. In the vast darkness of the deep ocean, where conventional approaches to vertebrate anatomy would mean starvation and death, evolution discovered a way to turn a mouth into an entire lifestyle. The Gulper eel is living proof that when survival is on the line, biology can become as creative and radical as any science fiction writer's imagination. As we continue to explore the deep ocean and encounter more of these impossible creatures, the Gulper eel stands as a reminder that our planet is far stranger and more creative than we ever imagined. It's a monster that shouldn't exist, a mouth with delusions of being a complete organism. Yet not only does it exist, it thrives, drifting through the abyss like a living question mark, challenging every assumption we have about what it means to be a vertebrate, a predator, and ultimately a successful form of life. Imagine stumbling across a pill bug the size of a small dog, its segmented body gleaming like medieval armor as it scuttles across an alien landscape. This isn't the premise of a science fiction horror film. It's the reality of encountering a giant isopod in the deep ocean. These creatures, reaching lengths of nearly 2 feet and weighing up to 4 pounds, represent one of the most striking examples of deep-sea gigantism, a phenomenon that challenges our understanding of how size and survival intersect in Earth's most extreme environments. Bathynomus giganteus, the largest member of the isopod family, is a creature that seems to have crawled directly out of the Paleozoic era. Its body plan has remained virtually unchanged for hundreds of millions of years, making it a living fossil that offers us a window into ancient oceans. Yet calling it a fossil is misleading. These are highly successful, perfectly adapted organisms that have found the perfect evolutionary strategy for survival in the abyss. If it works, don't change it. The giant isopod's armor-plated body is a marvel of biological engineering. Composed of overlapping segments called pleurites, this external skeleton provides protection that would make a knight envious. Each segment is precisely articulated with its neighbors, allowing the creature to curl into a perfect sphere when threatened, a defensive strategy known as conglobation. This ability to become a living ball isn't just for protection from predators. It also helps the isopod conserve heat and moisture, crucial adaptations for life in the cold, nutrient-poor depths. The construction of this armor reveals the sophisticated materials science that evolution has perfected over millions of years. The exoskeleton is composed primarily of chitin, the same material found in insect shells and crab claws, but in giant isopods. This chitin is arranged in complex layered structures that provide both flexibility and incredible strength. The outer layer is smooth and hard, designed to deflect attacks and reduce drag as the creature moves through the water. Beneath this lies a honeycomb structure that provides impact resistance while keeping the overall weight manageable. But the armor is more than just protection. It's a complete life support system. Embedded within the exoskeleton are sensory organs that can detect the slightest vibrations in the water, chemical receptors that can identify food sources from remarkable distances, and even specialized structures that help regulate the creature's internal pressure and temperature. The armor doesn't just protect the giant isopod, it actively helps it survive in one of Earth's most challenging environments. The phenomenon of deep-sea gigantism that giant isopods exemplify is one of the ocean's great mysteries. While most surface-dwelling arthropods are limited by the efficiency of their respiratory systems and the strength-to-weight ratios of their exoskeletons, deep-sea species routinely grow to sizes that would be impossible in shallow water. Giant isopods aren't the only examples. Deep-sea spider crabs can have leg spans approaching 12 feet, and amphipods in the deepest ocean trenches can reach sizes comparable to small lobsters. Several factors contribute to this gigantism. The cold temperatures of the deep ocean slow metabolic rates, meaning that giant isopods can afford to grow larger without requiring proportionally more food. The high pressure actually helps support larger body structures, reducing the structural stress that would make such size impossible at the surface. Perhaps most importantly, the stable environment of the deep sea means that giant isopods don't face the rapid environmental changes that force surface organisms to maintain more flexible, energy-efficient body plans. Giant isopods are the ultimate scavengers, playing a crucial ecological role as the cleanup crew of the deep ocean floor. Their feeding strategy is both patient and opportunistic. These creatures can survive for months or even years without food, entering a state of near hibernation where their already slow metabolism drops to barely detectable levels. When food does arrive, typically in the form of whale falls, large dead fish, or other organic matter that sinks from the surface waters, giant isopods can consume enormous quantities, sometimes eating so much that they become too heavy to move effectively. Their feeding apparatus is perfectly designed for their scavenging lifestyle. 4 sets of jaws work in coordination to tear apart tough organic matter, while powerful mandibles can crack through bones and shells that would defeat smaller scavengers. The digestive system is equally impressive, capable of breaking down organic matter that has been decomposing for weeks or months as it fell through the water column. Giant isopods can even digest cellulose and other plant materials that most marine scavengers cannot process, making them among the few deep-sea creatures capable of extracting nutrition from sunken wood and other terrestrial debris. The reproductive strategy of giant isopods reflects the resource-limited nature of their environment. Females carry their eggs in a specialized pouch called a marsupium, providing protection and nutrition to developing young in an environment where infant mortality would otherwise be catastrophically high. The eggs are enormous relative to the parent's body size, each one about the size of a grape, representing a massive investment of energy and resources. This strategy of producing fewer, larger, more developed offspring is common among deep-sea creatures, where the harsh environment makes survival of small, vulnerable young nearly impossible. Mating itself is a rare and complex process. Giant isopods may encounter potential mates only rarely in the vast emptiness of the deep ocean floor. When they do meet, courtship involves complex chemical communications and elaborate behavioral displays that can last for days. The male must convince the female that he's a worthy mate, while also ensuring that his genetic material will actually reach her eggs. No simple task when both animals are encased in armor plating. The sensory capabilities of giant isopods are another testament to their remarkable adaptation to deep-sea life. Their compound eyes, while small relative to their body size, are incredibly sensitive to the faintest traces of bioluminescent light. More importantly, they possess an array of chemical sensors that can detect organic compounds in concentrations so low they're barely measurable by our most sensitive instruments. A giant isopod can smell a dead whale from miles away, navigating through the featureless abyss to reach a food source that might sustain it for months. Their movement, while seemingly clumsy compared to sleek deep-sea fish, is actually precisely adapted to their lifestyle. Giant isopods are capable of surprisingly rapid scuttling when motivated by food or danger, their multiple legs providing stable locomotion across uneven seafloor terrain. They can also swim, though inefficiently, using rhythmic undulations of their body segments to propel themselves through the water column when necessary. Recent research has revealed that giant isopods play a more complex ecological role than previously understood. They're not just passive scavengers waiting for food to arrive. They're active ecosystem engineers. Their burrowing activities help aerate deep-sea sediments, creating microenvironments that support specialized bacterial communities. These bacteria, in turn, play crucial roles in deep-sea carbon cycling and nutrient processing. Giant isopods are also prey for larger deep-sea predators, making them an important link in food webs that we're only beginning to understand. The study of giant isopods has provided crucial insights into the limits and possibilities of arthropod body plans. Their success in the deep ocean demonstrates that the constraints we observe in surface-dwelling arthropods aren't fundamental biological limits, but rather environmental adaptations. Under the right conditions, stable temperature, high pressure, limited but predictable food sources, arthropods can achieve sizes and lifespans that rival those of vertebrates. From a biomaterials perspective, giant isopod armor represents a masterclass in composite design. Engineers studying their exoskeletons have gained insights into creating lightweight, flexible, yet incredibly strong materials for applications ranging from body armor to spacecraft hulls. The multi-layered structure, with its combination of rigid outer plates and flexible inner supports, has inspired new approaches to protective equipment design. The longevity of giant isopods is another remarkable aspect of their biology. While exact lifespans in the wild are difficult to determine, captive specimens have lived for decades, and there's evidence that wild individuals may live for over a century. This extreme longevity is partly due to their slow metabolism and low-stress environment, but it also reflects sophisticated cellular repair mechanisms that prevent the accumulation of damage that leads to aging in most organisms. Perhaps most remarkably, giant isopods represent evolutionary conservatism taken to an extreme. While most lineages undergo continuous evolutionary change in response to environmental pressures, giant isopods have found an ecological niche so perfectly suited to their anatomy and physiology that there's been virtually no selective pressure for change over hundreds of millions of years. They are living proof that sometimes the best evolutionary strategy is to perfect a design and stick with it. The deep-sea environment that giant isopods call home is both ancient and stable. While the surface ocean has undergone dramatic changes throughout Earth's history, ice ages, asteroid impacts, massive climate shifts, the deep ocean has remained remarkably consistent. This stability has allowed species like giant isopods to refine their adaptations over geological timescales, achieving levels of specialization that would be impossible in more dynamic environments. As we continue to explore the deep ocean, giant isopods serve as ambassadors from a world that operates by different rules than our surface-bound existence. They remind us that success in evolution isn't always about innovation and change. Sometimes it's about finding the perfect solution and maintaining it across eons. In their armored, ancient forms, we see not primitiveness, but perfection. Not evolutionary failure, but stunning success. Giant isopods are monsters in the truest sense. Creatures so alien to our experience that they challenge our basic assumptions about what life can be. Yet they're also marvels of engineering, examples of biological design principles refined over hundreds of millions of years. They shouldn't exist according to our surface world understanding of arthropod biology, yet they not only exist, but thrive in numbers that suggest they're among the most successful deep-sea animals on Earth. In the crushing darkness of the abyss, where life clings to existence by the thinnest of margins, giant isopods lumber through their domain like living tanks, proof that sometimes the best way to face an impossible world is to build an impenetrable shell and simply outlast everything else. They are living fossils, ancient mariners, and evolutionary masterpieces rolled into one armored, indestructible package, monsters that shouldn't exist, but absolutely do. In the vast blue wilderness of the open ocean, something exists that challenges the very concept of individuality. Stretching longer than a blue whale, yet thinner than a human hair in places, the Siphonophore is neither one creature nor many, but something entirely different. A colonial organism that blurs the boundaries between individual and collective, between simple and complex, between possible and impossible. To encounter a Siphonophore in its natural habitat is to witness something that seems to have emerged from the dreams of a cosmic intelligence. Picture a translucent ribbon of living glass drifting through the water column, pulsing with ethereal bioluminescent displays, its body a string of specialized units working in perfect harmony. Some sections pulse rhythmically to provide propulsion, others trail deadly tentacles hundreds of feet long, while still others focus on digestion, reproduction, or sensing the environment. It's as if someone took the organs of a conventional animal and spread them out along a living conveyor belt, creating a creature that exists in multiple dimensions simultaneously. The longest Siphonophore on record, belonging to the species Prior dubia, measured over 150 feet in length, longer than a blue whale, longer than most commercial aircraft, longer than many city blocks. Yet this massive organism began life as a single, microscopic larva no bigger than a grain of sand. The transformation from that tiny beginning to the sprawling colonial giant represents one of the most remarkable examples of biological self-assembly in the natural world. Understanding siphonophores requires abandoning conventional notions of what constitutes an individual organism. These creatures are colonies, but not in the way we typically think of colonies like coral reefs or ant nests. In those systems, individual organisms remain distinct even as they cooperate. Siphonophores have taken cooperation to such an extreme that the individual units, called zooids, cannot survive independently. They've become so specialized for their particular functions that they've essentially become organs of a larger superorganism. The architecture of a siphonophore is a masterpiece of biological engineering. At the front of the colony is the pneumatophore, a gas-filled float that provides buoyancy and, in some species, serves as a sail to catch ocean currents. Behind this come the swimming bells, specialized zooids that contract rhythmically to propel the colony through the water. These aren't random muscle contractions, but coordinated waves of movement that create efficient jet propulsion, pushing the entire colony forward with surprising grace and speed. Along the length of the colony, feeding polyps extend into the water, each one trailing tentacles armed with some of the most potent venom in the ocean. These tentacles can extend hundreds of times the length of the feeding polyp itself, creating a vast web of death that can capture prey across an enormous volume of water. The tentacles are lined with nematocysts, microscopic harpoons that inject neurotoxins, powerful enough to kill small fish instantly and cause excruciating pain to larger organisms, including humans. Interspersed among the feeding polyps are defensive zooids, specialized for protecting the colony from predators. These units can rapidly contract, pulling vulnerable parts of the colony away from danger, or they can release clouds of bioluminescent particles to confuse attackers. Still other zooids are devoted entirely to reproduction, developing the eggs and sperm that will create the next generation of these remarkable creatures. The coordination required to operate such a complex colonial system is staggering. A large siphonophore colony might contain millions of individual zooids, each specialized for a particular function, all working together with precision that would make a Swiss watch seem crude by comparison. There's no central brain controlling this coordination, no nervous system in the conventional sense. Instead, the colony relies on chemical signals and electrical impulses that travel through connecting tissues, creating a distributed intelligence that emerges from the collective behavior of the parts. This distributed intelligence allows siphonophores to respond to environmental changes with remarkable sophistication. When prey is detected by one part of the colony, chemical signals rapidly alert feeding polyps in the vicinity, causing them to extend their tentacles and position themselves optimally for capture. When a predator threatens one section of the colony, defensive responses are coordinated across the entire organism, with some parts contracting while others release deterrent chemicals or bioluminescent displays. The feeding strategy of siphonophores is as alien as their anatomy. Unlike conventional predators that actively hunt their prey, siphonophores are living fishing nets, drifting through the water column with their tentacles extended, waiting for prey to swim into their deadly embrace. But this passive approach is deceptive. Siphonophores can rapidly adjust their depth, speed, and orientation to position themselves in areas of high prey density. Some species coordinate their movements with daily vertical migrations of zooplankton, following their food source up and down through hundreds of feet of water column twice each day. When prey is captured, the feeding process reveals another layer of the siphonophore's remarkable biology. The tentacles contract, pulling the paralyzed victim toward a feeding polyp, where it's rapidly engulfed and digested. But the nutrients don't stay localized. They're distributed throughout the entire colony via a complex system of connecting channels. A fish captured at one end of a 100-foot siphonophore will provide nourishment to zooids at the opposite end, demonstrating a level of physiological integration that challenges our understanding of multicellular organization. The reproductive biology of siphonophores is equally extraordinary. Most species are simultaneous hermaphrodites with individual colonies containing both male and female reproductive zooids. When conditions are right, these specialized units release eggs and sperm into the water column where fertilization occurs. The resulting larvae are tiny, simple organisms that bear no resemblance to the complex colonies they will eventually become. Through a process called budding, these larvae gradually develop new zooids, each one specialized for a particular function, until the full colonial architecture is established. Some siphonophore species have evolved even more complex reproductive strategies. They can reproduce both sexually and asexually, sometimes releasing medusa, free-swimming reproductive stages that resemble tiny jellyfish. These medusa can travel far from the parent colony before releasing their gametes, helping to maintain genetic diversity across widely separated populations. The evolutionary history of siphonophores is a story of increasing colonial complexity. Their ancestors were simple, solitary organisms similar to modern jellyfish. Over millions of years, these creatures evolved the ability to form colonies through asexual reproduction, with individual offspring remaining attached to their parents. Initially, all members of these primitive colonies were identical, but gradually, different individuals began specializing for different functions. This division of labor became increasingly refined over evolutionary time, leading to the extraordinary level of specialization we see in modern siphonophores. The physics of siphonophore locomotion presents fascinating challenges and solutions. Moving a 150-foot-long, extremely fragile organism through the water without tearing it apart requires sophisticated biomechanical strategies. The swimming bells don't all contract simultaneously. Instead, waves of contraction travel along the colony, creating undulating motions that minimize stress on the connecting tissues. The entire system is remarkably efficient, allowing massive colonies to move through the water with minimal energy expenditure. Bioluminescence plays multiple roles in siphonophore biology. Many species can create spectacular light displays with waves of illumination traveling along the length of the colony. These displays serve various functions. They can startle predators, attract prey, or serve as communication signals between different parts of the colony or between separate colonies. The light-producing organs are often among the most beautiful structures in the natural world, resembling strings of living jewels arranged along the translucent body of the colony. The ecological impact of siphonophores is far greater than their ethereal appearance might suggest. As some of the ocean's most efficient predators, they play crucial roles in marine food webs. A single large colony can consume thousands of small fish, crustaceans, and other organisms each day, making them among the most significant predators in the open ocean, despite their fragile appearance. Recent research has revealed that siphonophores are far more abundant than previously thought. Advanced underwater imaging technology has shown that these creatures exist in vast numbers throughout the world's oceans, forming what some researchers describe as living curtains that span hundreds of square miles. Their combined predation pressure may be comparable to that of all the ocean's fish combined. Yet because they're translucent and fragile, they've remained largely invisible to traditional sampling methods. The study of siphonophores has profound implications for our understanding of biological organization and complexity. These creatures demonstrate that the evolution of multicellularity isn't limited to the single pathway that led to plants, animals, and fungi. Instead, siphonophores represent an alternative solution to the challenge of creating complex, large organisms, one based on colonial integration rather than cellular differentiation. From a biomimetics perspective, Siphonophores offer insights into distributed robotics and autonomous systems. Their ability to coordinate complex behaviors without centralized control has inspired research into swarm robotics, where large numbers of simple units work together to accomplish tasks that would be impossible for any individual unit. The modular design of Siphonophore colonies, where specialized units can be added or removed as needed, provides a model for adaptive engineering systems. The fragility of Siphonophores also makes them sensitive indicators of ocean health. These creatures are among the first to be affected by changes in water temperature, chemistry, or currents. Climate change, ocean acidification, and pollution all impact Siphonophore populations, making them valuable sentinels for monitoring the health of marine ecosystems. Perhaps most remarkably, Siphonophores force us to reconsider fundamental questions about identity and consciousness. If a Siphonophore colony containing millions of specialized units can coordinate complex behaviors, hunt efficiently, and respond appropriately to environmental challenges, what does this tell us about the nature of intelligence and awareness? These creatures exist at the boundary between the individual and the collective, challenging our anthropocentric notions of what it means to be a conscious entity. In the vast theater of the open ocean, Siphonophores perform their alien ballet, stretching their translucent forms through dimensions that conventional organisms cannot occupy. They are living proof that evolution's creativity knows no bounds, that life can organize itself in ways that defy our expectations and expand our understanding of what's possible. They shouldn't exist according to our conventional understanding of animal organization. Yet they not only exist, they thrive as some of the ocean's most successful predators, invisible masters of the blue wilderness. In the darkest depths of the ocean's twilight zone, where the last traces of sunlight fade into eternal night, dwells a creature so bizarre that early researchers couldn't decide what it was. With a name that evokes gothic horror and an appearance that seems designed by a committee of nightmare artists, the vampire squid represents one of evolution's most enigmatic experiments, a living fossil that occupies its own unique branch on the tree of life. Vampiroteuthis infernalis, literally vampire squid from hell, earned its dramatic name from early specimens that arrived at the surface with their dark webbing spread like a Victorian villain's cape and their eyes glowing with an otherworldly red luminescence. But despite its fearsome moniker, the vampire squid is neither a true squid nor an octopus, and it's certainly not a vampire. Instead, it's something far stranger, a relic from an ancient evolutionary lineage that has survived in the deep ocean for over 300 million years, watching the rise and fall of dinosaurs from the safety of the abyss. The vampire squid's body plan seems assembled from the spare parts of other cephalopods. Like an octopus, it has 8 arms connected by a web of dark tissue, but unlike any octopus, it can turn itself completely inside out, inverting its body so that its arms point backward and its protective spines face outward. This transformation, called pineapple posture by researchers, turns the creature into a living fortress of spikes and defensive chemicals, a strategy so alien that it took decades for scientists to understand what they were witnessing. But the most remarkable feature of the vampire squid isn't visible in its defensive posture. It's the pair of retractile filaments that can extend from pockets near the base of its arms. These structures, called cirri, are unlike anything found in other cephalopods. They can stretch to twice the length of the creature's body, equipped with tiny hooks and sensory organs that allow the vampire squid to explore its environment and capture food without exposing its vulnerable body. When not in use, these filaments disappear completely into their protective pouches, ready to be deployed at a moment's notice. The eyes of the vampire squid are perhaps its most striking feature, proportionally the largest eyes of any animal on Earth, relative to body size. These massive sensory organs, glowing with an eerie blue bioluminescence, can be over an inch in diameter on a creature whose body is only 6 inches long. This extreme eye development makes sense in the perpetual twilight of the vampire squid's habitat, where the ability to detect the faintest traces of light can mean the difference between finding food and starving. The vampire squid's habitat is one of the most extreme environments on our planet, the oxygen minimum zone, where dissolved oxygen levels drop so low that most marine life cannot survive. This layer, typically found between 2,000 and 3,000 feet below the surface, contains less than 2% of the oxygen found in surface waters. For most animals, entering this zone means rapid death by suffocation. For the vampire squid, it's home sweet home. Surviving in such low oxygen conditions requires extraordinary physiological adaptations. The vampire squid's metabolism operates at a rate so slow it seems almost suspended. Its heart beats just a few times per minute. Its movements are deliberate and economical, and it can enter states of near hibernation that last for days or weeks. The creature's blood contains specialized hemocyanin proteins that are incredibly efficient at capturing and holding on to oxygen molecules, allowing it to extract usable oxygen from water that would be lethal to other animals. But perhaps the most alien aspect of vampire squid biology is its feeding strategy. Unlike the active predators of the squid and octopus families, vampire squids are primarily detritivores. They feed on marine snow, the constant rain of organic particles that drifts down from the productive surface waters above. Using its extendable filaments, the vampire squid collects these particles and packages them into boluses of concentrated nutrition using mucus secretions. This feeding strategy is so unusual among cephalopods that it took researchers decades to understand how these creatures were surviving in their nutrient-poor environment. The marine snow diet of vampire squids consists of a bizarre mixture of organic materials, dead plankton, fecal pellets from surface-dwelling animals, fragments of larger organisms, and even terrestrial plant matter that has somehow made its way into the ocean. This detritus might seem unappetizing, but it represents a vast and relatively untapped food resource. While other deep-sea predators compete for the rare live prey that ventures into their realm, vampire squids have evolved to exploit the steady rain of organic matter that most other animals ignore. The reproductive strategy of vampire squids reflects the extreme constraints of their environment. Females invest enormous energy into producing a small number of large eggs, each one representing a significant portion of the mother's total body mass. These eggs are among the largest of any cephalopod relative to adult body size, providing developing embryos with enough nutrition to survive the harsh conditions of the deep ocean. The brooding period is exceptionally long, up to 400 days in some cases, during which the female provides constant care and protection to her developing offspring. Mating in vampire squids is a mysterious process that occurs in the eternal darkness of their deep-sea habitat. Males are equipped with specialized reproductive organs that can transfer packets of sperm to females, but the details of their courtship behavior remain largely unknown. The sparse population density in their habitat means that encounters between potential mates are rare and precious, leading to complex behavioral adaptations that maximize the chances of successful reproduction when opportunities arise. The bioluminescent capabilities of vampire squids are among the most sophisticated in the animal kingdom. They possess multiple light-producing organs distributed across their body, each one capable of producing different colors and intensities of light. These photophores can create complex displays, flashing sequences, color changes, and patterns of illumination that may serve as communication signals, predator deterrents, or prey lures. Some vampire squids can even eject clouds of bioluminescent particles, creating confusion displays that allow them to escape from predators. The evolutionary history of vampire squids provides fascinating insights into the ancient origins of cephalopod intelligence. Fossil evidence suggests that the vampire squid lineage diverged from other cephalopods over 300 million years ago, during the Carboniferous period when the first forests were forming on land. While their squid and octopus relatives evolved into active predators with complex behaviors and remarkable intelligence, vampire squids took a different path, becoming highly specialized for survival in one of Earth's most challenging environments. This ancient lineage has remained remarkably stable over geological time. Fossil vampire squids from 200 million years ago are nearly identical to modern specimens, suggesting that these creatures achieved an optimal body plan early in their evolution and have had little selective pressure to change. They are living links to an ancient world, survivors from a time when the ocean's chemistry and circulation patterns were dramatically different from today. The nervous system of vampire squids shows intriguing similarities to both squid and octopus brains, but with unique features that reflect their specialized lifestyle. Their brains are proportionally smaller than those of their more active relatives, but they contain specialized regions devoted to processing sensory information from their unique filaments and managing their complex bioluminescent displays. Recent research suggests that vampire squids may be more intelligent than their sluggish behavior suggests, with problem-solving abilities that help them navigate the complex, three-dimensional environment of the deep ocean. The study of vampire squids has provided crucial insights into the limits of multicellular life. These creatures exist at the very edge of what's physiologically possible for complex animals, surviving in conditions that would quickly kill most other organisms. Their success in such extreme conditions demonstrates the remarkable plasticity of life, showing how evolution can find solutions to seemingly impossible challenges. From a biomimetics perspective, vampire squid adaptations are inspiring new technologies for extreme environment exploration. Their oxygen-efficient metabolism is informing research into life support systems for deep-sea and space exploration. Their bioluminescent communication systems are being studied for applications in underwater robotics and remote sensing. Even their unique feeding strategy, collecting dispersed particles using extended appendages, has applications in environmental monitoring and resource extraction technologies. The vampire squid's ability to completely invert its body structure has particular relevance for soft robotics research. Engineers are studying how the creature manages to turn itself inside out without damage, hoping to develop new types of flexible, transformable machines. The defensive spines that emerge during this transformation are being investigated as models for adaptive armor systems that can change configuration in response to different types of threats. Climate change poses unique challenges for vampire squids. As ocean temperatures rise and circulation patterns change, the boundaries of the oxygen minimum zones where these creatures live are shifting. Some populations may benefit from expanding low oxygen regions, while others may find their habitat compressed or eliminated entirely. Because vampire squids have such specific environmental requirements and slow reproductive rates, they may be particularly vulnerable to rapid environmental changes. The discovery of vampire squids has also challenged traditional taxonomic classifications. These creatures are so unique that they required the creation of an entirely new order, Vampiromorpha, to accommodate their distinctive characteristics. They represent one of the few examples of a living fossil that isn't actually closely related to any known fossil species, instead representing a relic lineage that has survived in isolation for hundreds of millions of years. Recent advances in deep-sea observation technology have begun to reveal new aspects of vampire squid behavior and ecology. High-definition cameras mounted on remotely operated vehicles have captured footage of these creatures in their natural habitat, showing behaviors that were impossible to observe in laboratory settings. These observations have revealed that vampire squids are more active and behaviorally complex than previously thought, engaging in subtle social interactions and complex foraging strategies that were invisible to earlier research methods. The vampire squid's unique position in the cephalopod family tree also provides insights into the evolution of intelligence in marine organisms. By comparing the neurological and behavioral capabilities of vampire squids with those of their more familiar squid and octopus relatives, researchers are beginning to understand how different environmental pressures shape the evolution of cognitive abilities. The vampire squid's specialized intelligence, adapted for surviving in extreme conditions rather than active predation, represents an alternative pathway for the evolution of complex behaviors in marine environments. In the crushing darkness of the ocean's twilight zone, vampire squids drift like living ghosts, their massive eyes scanning for threats and opportunities in a world where both are rare and precious. They are evolutionary anachronisms, survivors from an ancient ocean, perfectly adapted to conditions that would mean death for virtually any other complex animal. They shouldn't exist according to our understanding of animal physiology and the limits of multicellular life. Yet they not only exist, they represent one of the most successful deep-sea lineages on Earth. The vampire squid is a reminder that evolution doesn't always favor speed, strength, or conventional intelligence. Sometimes the most successful strategy is to find an impossible niche and master it completely, to become so perfectly adapted to extreme conditions that you face no competition whatsoever. In their dark realm, vampire squids have achieved something remarkable. They've become the undisputed masters of the impossible, living proof that life will find a way to thrive, even at the very edges of what we consider possible. In the perpetual twilight of the deep ocean, where the last whispers of sunlight fade into absolute darkness, swims a fish so bizarre that early specimens were dismissed as damaged curiosities. The Barreleye fish, with its transparent head and tubular eyes that can rotate like periscopes, represents one of evolution's most radical experiments in sensory adaptation, a creature that has literally developed windows in its skull to better navigate the alien world of the deep sea. Macropinna microstoma, the most well-known member of the Barreleye family, appears at first glance to be the victim of some cruel cosmic joke. Its head is completely transparent, a living snow globe filled with clear fluid through which its bright green eyes are clearly visible, pointing upward like biological telescopes. The fish's actual eyes aren't where you'd expect them to be. The dark spots that appear to be eyes at the front of its head are actually its nostrils. This anatomical confusion initially led researchers to believe that specimens had been damaged during collection, their delicate structures destroyed by the trauma of being brought to the surface. It took decades of research and the development of sophisticated deep-sea observation techniques to reveal the true nature of the Barreleye's extraordinary anatomy. The transparent head, far from being a sign of damage, is actually a marvel of biological engineering, a fluid-filled shield that protects the fish's tubular eyes while allowing them complete freedom of movement. These eyes can rotate within the transparent dome of the head, pointing forward to look for prey or upward to scan for the silhouettes of potential meals against the faint light filtering down from above. The eyes themselves are unlike those of any other vertebrate. Rather than the spherical eyes we're familiar with, Barreleye fish have developed tubular eyes that function more like biological telescopes. These structures are packed with an enormous number of light-sensitive cells, making them incredibly efficient at gathering the minute traces of light available in the deep ocean. The tubular shape also provides exceptional directional vision, allowing the fish to determine precisely where faint light sources are located in the three-dimensional darkness around them. The transparent head that houses these remarkable eyes is filled with a clear, gelatinous substance that has the same refractive index as seawater. This means that light passes through the head with virtually no distortion, providing the fish with an unobstructed view of its surroundings. The dome itself is incredibly thin and delicate, yet strong enough to withstand the crushing pressure of the deep ocean. It's essentially a biological window, evolved to give the barreleye fish capabilities that seem more like science fiction than natural history. But the barreleye's adaptations go far beyond its extraordinary visual system. The fish's body is laterally compressed and covered with large, thin scales that give it an almost ethereal appearance. Its fins are positioned and shaped to provide precise maneuvering capability rather than speed, allowing the fish to maintain exact positions in the water column while it hunts. The mouth is small and positioned to capture small prey items with surgical precision, reflecting the fish's specialized feeding strategy. Barreleye fish are ambush predators that have evolved to exploit one of the deep ocean's most abundant but difficult to catch food sources: the gelatinous animals that drift through the water column. Siphonophores, jellies, and other soft-bodied creatures are nearly invisible to most predators. But the barreleye's extraordinary visual system allows it to detect these transparent prey items against the faint background light. The fish positions itself below its intended prey and uses its rotating eyes to track the target's movements before making a precisely timed vertical strike. This hunting strategy requires extraordinary patience and energy efficiency. Barreleye fish may remain motionless for hours at a time, maintaining their position in the water column while their eyes constantly scan the waters above. When prey is detected, the attack must be swift and accurate. There are no second chances in the energy-limited environment of the deep sea. The fish's entire anatomy is optimized for these brief moments of predatory action, with every system designed to maximize the efficiency of capturing elusive prey. The bioluminescent capabilities of barreleye fish add another layer to their alien appearance. Many species possess photophores that can produce light displays along their bodies, though the function of these lights in such a specialized visual predator remains somewhat mysterious. Some researchers believe the lights may be used for communication between individuals or as a form of counter-illumination camouflage, helping the fish blend in with the faint light filtering down from above. The reproductive biology of barreleye fish reflects the challenges of life in the deep ocean. These fish are believed to be broadcast spawners, releasing eggs and sperm into the water column where fertilization occurs. The larvae that develop from these eggs are dramatically different from the adults, with conventional-looking heads and eyes that gradually transform as the fish matures. This metamorphosis is one of the most dramatic in the fish world, with the young fish essentially rebuilding its entire head structure as it develops its specialized adult anatomy. The evolutionary history of barreleye fish provides insights into how extreme specialization can arise in stable environments. These fish belong to the family Opisthoproctidae, which diverged from other fish lineages approximately 50 million years ago. The development of their transparent heads and tubular eyes represents a relatively recent evolutionary innovation, suggesting that the deep-sea environment has remained stable enough over this time period to favor increasingly specialized adaptations. Recent genetic studies have revealed that barreleye fish possess unique modifications to the genes that control eye development. The proteins that normally create the rigid structure of vertebrate skulls have been modified in these fish to produce the transparent, flexible dome that houses their eyes. This represents a dramatic rewiring of fundamental developmental processes, showing how evolution can repurpose basic body plans to create entirely new capabilities. The study of Barreleye fish has important implications for our understanding of sensory biology and the limits of vertebrate anatomy. These fish demonstrate that even fundamental features like skull structure can be radically modified when the selective pressures are strong enough. Their transparent heads represent a solution to the problem of maximizing visual capability in an extremely light-limited environment, showing how evolution can overcome seemingly insurmountable anatomical constraints. From a biomimetics perspective, Barreleye fish are inspiring new approaches to optical instrument design. Their tubular eyes, with their exceptional light-gathering capability and precise directional sensitivity, are being studied as models for low-light imaging systems and astronomical telescopes. The transparent dome structure is informing research into protective housings for delicate optical equipment that must function in extreme environments. The Barreleye's ability to rotate its eyes independently within the protective dome has particular relevance for robotic vision systems. Engineers are developing new types of cameras and sensors that can mimic this capability, allowing robotic systems to scan their environment without having to move their entire body. This has applications ranging from underwater exploration vehicles to spacecraft sensors that must track multiple targets simultaneously. Climate change and human activities pose unique threats to Barreleye fish populations. These highly specialized predators depend on the complex food webs of the deep ocean, which are increasingly disrupted by warming temperatures, changing ocean chemistry, and pollution. Their prey species, the delicate gelatinous animals of the water column, are particularly sensitive to environmental changes, meaning that disruptions to these ecosystems could have cascading effects on Barreleye populations. The discovery and study of Barreleye fish has also highlighted the importance of developing new techniques for studying deep-sea organisms in their natural habitat. Traditional sampling methods, which involved bringing specimens to the surface in nets, were completely inadequate for understanding these delicate creatures. Only with the development of sophisticated, remotely operated vehicles equipped with high-definition cameras and gentle collection systems could researchers begin to appreciate the true nature of Barreleye anatomy and behavior. Recent observations of living Barreleye fish in their natural habitat have revealed behaviors that were impossible to study in laboratory settings. High-definition video footage has shown these fish engaged in complex hunting behaviors, social interactions, and even possible territorial disputes. These observations are gradually building a more complete picture of how these extraordinary creatures live and interact in their deep-sea environment. The Barreleye fish's visual system also provides insights into the evolution of consciousness and sensory experience. With their massive, highly developed eyes and complex behaviors, these fish clearly have rich sensory experiences of their environment. Yet their sensory world is so different from our own, dominated by the detection of faint light sources and transparent prey in three-dimensional darkness, that it challenges us to imagine what their subjective experience might be like. The neurological processing required to integrate information from rotating, tubular eyes with input from other sensory systems is extraordinarily complex. Barreleye fish brains show specialized enlargement of the visual processing regions, suggesting that a significant portion of their neural capacity is devoted to processing the detailed information gathered by their extraordinary eyes. This neural specialization has evolved specifically to support their unique lifestyle, representing another example of how extreme environments can drive the evolution of specialized cognitive capabilities. In the vast darkness of the deep ocean, Barreleye fish drift like living spacecraft, their transparent heads gleaming with an otherworldly beauty as their green eyes scan the water above for signs of prey. They are evolutionary poets, creatures whose very existence seems to challenge the boundaries between the biological and the mechanical, between the natural and the supernatural. They shouldn't exist according to our conventional understanding of vertebrate anatomy, yet they not only exist, they've mastered one of the most challenging predatory niches in the ocean. The Barreleye fish is a reminder that evolution's creativity knows no bounds, that given enough time and the right selective pressures, life can develop solutions that seem to come from the realm of imagination rather than biology. In their transparent heads and rotating eyes, we see not just remarkable adaptations, but windows into the infinite possibilities that arise when life confronts the impossible and refuses to back down. They are monsters of beauty rather than horror, aliens that call our own planet home, living proof that the natural world will always be stranger and more wonderful than we dare to imagine. In the crushing darkness of the deep ocean, where volcanic vents tear through the sea floor and spew toxic chemicals into the frigid water, lives a creature so unexpected that its discovery rewrote our understanding of where life can exist. The Yeti crab, with its arms covered in dense mats of bacteria-like filaments, represents one of evolution's most recent and remarkable innovations. A creature that has learned to farm its own food in one of the most hostile environments on Earth. Kiwa hirsuta, the first Yeti crab discovered in 2005, was found living directly on the rim of hydrothermal vents 7,200 feet below the surface of the Pacific Ocean. These vents, essentially underwater geysers that spew superheated water loaded with toxic chemicals, create conditions that should be absolutely lethal to complex life. Water temperatures can exceed 750 degrees Fahrenheit, hot enough to melt lead, while the chemical cocktail includes hydrogen sulfide, methane, and heavy metals that would poison most organisms instantly. Yet here, in this underwater hell, the Yeti crab not only survives, but thrives. The most striking feature of the Yeti crab is the dense covering of filamentous structures that coat its claws and legs, giving it an appearance that immediately evokes the legendary abominable snowman. But these aren't hairs in any conventional sense. They're something far stranger and more sophisticated. These filaments host vast colonies of bacteria that form a living, breathing ecosystem right on the crab's body. The crab has essentially become a walking farm, cultivating its food supply in the form of bacterial gardens that cover its appendages. This bacterial farming represents one of the most intimate symbiotic relationships known in the animal kingdom. The bacteria living on the Yeti crab's filaments are chemosynthetic organisms capable of deriving energy from the toxic chemicals that pour out of hydrothermal vents. They convert hydrogen sulfide, methane, and other compounds that would be deadly to most life forms into organic matter that serves as food for both the bacteria themselves and their crab host. In return, the crab provides the bacteria with a mobile platform that can position them optimally within the chemical gradients around the vents. The relationship between Yeti crab and bacteria is so intimate that neither partner can survive without the other. The bacteria have become so specialized for life on the crab that they cannot exist independently in the environment, while the crab depends entirely on its bacterial partners for nutrition. This represents an evolutionary partnership that has moved beyond simple cooperation into true biological integration, where the boundaries between the two organisms become blurred. The farming behavior of Yeti crabs is as sophisticated as any human agricultural practice. The crabs actively tend their bacterial gardens, waving their hairy arms through the chemical-rich water around hydrothermal vents to provide their bacterial partners with optimal exposure to the nutrients they need. Different species of Yeti crabs have evolved different farming techniques. Some position themselves to catch the plumes of chemicals rising from active vents, while others move constantly to maintain their bacterial gardens within narrow temperature and chemical zones. Recent research has revealed that Yeti crabs actively harvest their bacterial crops, scraping the filaments with specialized mouthparts to consume the excess bacterial growth. This harvesting must be carefully managed. Take too much and the bacterial colonies collapse, leaving the crab without its primary food source. Take too little and the overgrown bacteria may become less efficient at processing the chemical nutrients they depend on. The crab has evolved behavioral strategies that maintain this delicate balance, essentially practicing sustainable agriculture at the cellular level. The discovery of Yeti crabs has forced scientists to reconsider the limits of complex life on Earth. Hydrothermal vents were once thought to be the exclusive domain of simple bacteria and archaea, single-celled organisms that could tolerate the extreme chemical and temperature conditions. The presence of complex animals like Yeti crabs, with their sophisticated behaviors and intricate symbiotic relationships, demonstrates that even the most extreme environments on our planet can support remarkable biodiversity. The anatomy of Yeti crabs reflects their adaptation to life in one of Earth's most challenging environments. Their shells are thinner than those of most crabs, an adaptation that helps them cope with the extreme pressure differences between the hot vent water and the frigid surrounding ocean. Their internal organs have been modified to process the unusual diet provided by their bacterial partners, with digestive systems that can extract nutrition from bacterial biomass while filtering out the toxic compounds that permeate their environment. The sensory systems of Yeti crabs are equally remarkable. Living in absolute darkness, these creatures have reduced or absent eyes, but they've developed extraordinary chemical sensing capabilities. They can detect minute changes in the chemical composition of the water around them, using this information to navigate between different vent sites and maintain optimal positions for their bacterial farming activities. Some species have developed specialized sensory structures that can detect temperature gradients, helping them avoid the lethal heat of active vents, while staying close enough to provide their bacteria with necessary chemicals. The reproductive strategies of Yeti crabs are constrained by their extreme habitat requirements. Females must find ways to protect their eggs in an environment where temperature fluctuations could easily kill developing embryos. Some species brood their eggs away from the most active vent sites, while others have evolved eggs with extraordinary resistance to temperature extremes. The larvae face the challenge of finding new vent sites in the vast darkness of the deep ocean, often traveling hundreds of miles through water that cannot support their specialized lifestyle. The evolutionary history of Yeti crabs represents one of the most rapid adaptive radiations known in the animal kingdom. The first hydrothermal vents were only discovered in 1977, yet genetic evidence suggests that Yeti crabs began specializing for vent life relatively recently in geological terms. This rapid evolution demonstrates how quickly life can adapt to new ecological opportunities when the selective pressures are strong enough. Different species of Yeti crabs have evolved distinct strategies for exploiting hydrothermal vent environments. Kiwa puravida, discovered in 2006, lives in methane seeps rather than sulfide vents, requiring different bacterial partners and farming techniques. Kiwa tyleri, found in 2010, lives in such dense aggregations around Antarctic vents that they form living carpets covering the seafloor, with hundreds of individuals packed together in spaces smaller than a kitchen table. The discovery of these dense Yeti crab populations has revealed new insights into the social behavior of deep-sea creatures. Unlike most crabs, which are typically solitary or form only loose aggregations, some Yeti crab species live in highly organized communities. These aggregations may serve multiple functions. They could help individuals share chemical information about optimal farming locations, provide protection from the few predators that can tolerate vent environments, or create more favorable microclimates for bacterial cultivation. The chemical ecology of Yeti crab habitats is extraordinarily complex. Hydrothermal vents create steep gradients of temperature, pH, oxygen levels, and toxic compounds across distances of just inches. Yeti crabs must navigate these gradients with precision, positioning themselves and their bacterial partners in the narrow zones, where conditions are optimal for both crab survival and bacterial productivity. This requires constant behavioral adjustments as vent conditions change over time, scales ranging from minutes to years. The bacterial partners of Yeti crabs represent some of the most extreme organisms on Earth. These bacteria can tolerate temperatures that would denature most proteins, pH levels that would dissolve conventional biological structures, and concentrations of toxic compounds that would kill most known life forms. Yet they're also highly productive, converting the chemical energy available at vents into biological matter at rates that rival the most fertile surface ecosystems. Recent advances in molecular biology have revealed the extraordinary diversity of bacteria living on Yeti crabs. A single individual may host dozens of different bacterial species, each specialized for processing different chemical compounds or thriving under different environmental conditions. This bacterial diversity provides the crab with a flexible food production system that can adapt to the changing chemical conditions around hydrothermal vents. The study of Yeti crabs has important implications for astrobiology and the search for life in extreme environments throughout the universe. The ability of these creatures to thrive in conditions that seem utterly hostile to life demonstrates that complex ecosystems can exist in environments far more extreme than previously thought possible. This expands our understanding of where life might exist on other planets, particularly in the subsurface oceans of moons like Europa and Enceladus. From a biotechnology perspective, the bacterial partners of Yeti crabs represent a treasure trove of potentially useful organisms. Bacteria that can thrive in extreme temperature and chemical conditions have applications in industrial processes, environmental cleanup, and pharmaceutical production. The enzymes produced by these bacteria, which function at temperatures and pH levels that would destroy conventional biological molecules, are of particular interest for developing new biotechnological applications. The conservation challenges facing Yeti crab populations are unique among marine organisms. These creatures are entirely dependent on hydrothermal vent habitats, which are themselves ephemeral features that can appear and disappear on timescales of years to decades. As vents become inactive, the specialized ecosystems they support collapse, forcing Yeti crabs and other vent-dependent organisms to colonize new sites or face local extinction. Human activities pose additional threats to Yeti crab populations. Deep-sea mining operations targeting the mineral-rich deposits around hydrothermal vents could destroy critical habitat for these specialized creatures. The polymetallic sulfides that form around vents contain valuable metals like copper, gold, and silver, making them attractive targets for commercial exploitation. Balancing the economic value of these resources with the conservation needs of unique vent ecosystems presents unprecedented challenges for marine management. Climate change may also impact Yeti crab populations. though in ways that are difficult to predict. Changes in ocean circulation patterns could affect the distribution and intensity of hydrothermal activity, potentially altering the availability of suitable habitat for these specialized creatures. Ocean acidification, driven by increasing atmospheric carbon dioxide, could affect the chemical conditions around vents in ways that disrupt the delicate balance between Yeti crabs and their bacterial partners. The study of Yeti crabs continues to yield surprises that challenge our understanding of life in extreme environments. Recent discoveries include species that cultivate different types of bacteria on different parts of their bodies, essentially practicing crop rotation at the microscopic level. Other species have been found to engage in complex behaviors that suggest they may communicate with each other through chemical signals, coordinating their farming activities across entire vent communities. In the hellish landscape of hydrothermal vents, where toxic chemicals mix with superheated water and crushing pressure creates conditions that seem utterly hostile to life. Yeti crabs wave their bacterial gardens like living prayer flags, farming food from poison and finding abundance in scarcity. They are biological alchemists, creatures that have learned to transmute the toxic waste products of the Earth's interior into the building blocks of life. They shouldn't exist according to our understanding of where complex life can survive. Yet they not only exist, they've created thriving agricultural communities in environments more extreme than anything found on the surface of our planet. The Yeti crab is a reminder that life's creativity and adaptability know no bounds. In the most unlikely places, under the most impossible conditions, evolution continues to find ways to not just survive but prosper. These creatures represent the cutting edge of life's expansion into every possible niche on our planet. Pioneers of impossibility who have made homes in hell itself. They are monsters of resilience rather than terror, living proof that there is no environment so extreme, no condition so hostile, that life cannot find a way to transform it into an opportunity for growth and abundance. As we surface from our journey into the abyss, leaving behind the crushing darkness and the creatures that call it home, we carry with us more than just knowledge of strange animals. We carry a fundamentally altered understanding of what life can be. The monsters we've encountered in the deep ocean aren't just biological curiosities to be catalogued and filed away. They are revolutionary teachers, showing us that every assumption we've made about the limits and possibilities of life on Earth needs to be reconsidered. The Gulper eel, with its impossible mouth and thread-thin body, teaches us that anatomical rules we consider fundamental are actually just suggestions. In the deep ocean, where food is scarce and opportunities rare, evolution has discovered that sometimes the best strategy is to become mostly mouthy, to transform the very concept of what it means to be a vertebrate. The eel's success challenges our surface world assumptions about efficient body design and shows us that efficiency itself must be redefined based on environmental context. Giant isopods lumbering through the abyss like living fossils in perfect armor demonstrate that evolutionary conservatism can be just as successful as innovation. While we often celebrate evolution's creativity and constant change, these ancient mariners remind us that sometimes the best response to environmental challenges is to perfect a design and maintain it across geological time. Their existence proves that there are solutions so elegant, so perfectly suited to their environment, that they transcend the need for change. The Siphonophores, those impossible colonial organisms that blur the boundaries between individual and collective, force us to reconsider the very nature of identity and consciousness. In their distributed intelligence and modular bodies, we see glimpses of organizational strategies that might represent the future of both biological and technological systems. They are living demonstrations that complexity can emerge from cooperation, that intelligence doesn't require centralization, and that the boundaries between self and other are far more fluid than our human-centric perspective suggests. The vampire squid, ancient and alien in its oxygen-starved realm, shows us that life can persist at the very edges of what we consider possible. Its survival in conditions that would kill virtually any other complex animal demonstrates that the limits we perceive for life are often limits of our own imagination, rather than genuine biological constraints. In its patient endurance and radical efficiency, we see a template for survival that may become increasingly relevant as our own planet faces environmental challenges. Barreleye fish, with their transparent heads and rotating eyes, prove that even fundamental features like skull structure can be radically reimagined when the selective pressures are strong enough. Their living windows into the deep ocean remind us that evolution is not constrained by our preconceptions about what vertebrate anatomy can or should look like. They are biological impossibilities made manifest, creatures whose very existence expands our understanding of what complex life can achieve. The Yeti crab, farming bacteria on toxic chemicals at the edge of underwater volcanoes, represents perhaps the most profound lesson of all, that life doesn't just adapt to extreme environments, it transforms them into opportunities. In their bacterial gardens and chemical agriculture, we see life's ultimate triumph over adversity, the conversion of poison into sustenance, of hostility into hospitality. Together, these creatures paint a picture of a planet far stranger and more creative than we ever imagined. They exist in a realm that covers more than 60% of Earth's surface, yet remains less explored than the surface of Mars. In this vast underwater universe, evolution has been conducting experiments that challenge every biological principle we thought we understood. The results of these experiments are swimming, crawling, drifting, and farming their way through environments that shouldn't support complex life, using strategies that shouldn't work, with anatomies that shouldn't be possible. But perhaps the most profound impact of encountering these deep-sea monsters is philosophical rather than scientific. They humble us in our surface world existence, surrounded by familiar forms of life that conform to patterns we can understand and predict. It's easy to develop an inflated sense of our own understanding of biology and life itself. The creatures of the deep ocean strip away this comfortable familiarity and force us to confront the reality that we are just one expression of life among millions of possibilities we haven't even discovered yet. These monsters that shouldn't exist also serve as ambassadors from a future we're only beginning to glimpse. As we push the boundaries of technology and exploration, as we contemplate life in space and the development of artificial intelligence, the solutions that evolution has already discovered in the deep ocean offer blueprints for innovations we haven't even dreamed of yet. The distributed intelligence of Siphonophores, the pressure-resistant design of deep-sea creatures, the chemical farming of Yeti crabs, the optical systems of Barreleye fish, all of these represent technologies that could transform our approach to engineering, medicine, computing, and space exploration. Yet even as we study these creatures for their practical applications, we must remember that their greatest value may be in what they teach us about the nature of life itself. They are reminders that our planet is far from fully explored, that new forms of organization and existence are still being discovered, and that life's creativity and resilience far exceed our ability to predict or control it. The deep ocean that these creatures call home is changing. Human activities are altering ocean chemistry, temperature, and circulation patterns in ways that could profoundly impact deep-sea ecosystems. Climate change, pollution, and deep-sea mining threaten habitats that took millions of years to develop and support creatures found nowhere else on Earth. Many of these species reproduce slowly, live at low population densities, and depend on stable environmental conditions that may not persist as human impacts on the ocean intensify. The urgency of protecting these alien realms and their inhabitants cannot be overstated. We are likely losing species faster than we can discover them, watching entire ecosystems disappear before we've had the chance to understand what they might teach us. Every deep-sea expedition brings back new species, new forms of organization, new solutions to the challenges of existence that we never imagined possible. Yet for every creature we discover, dozens or hundreds more may be vanishing unnoticed into extinction. The monsters of the deep ocean also serve as powerful reminders of how much we still don't know about our own planet. We live on a water world, yet we've explored less than 5% of our ocean. We know more about the surface of the moon than about the deepest parts of our own seas. In an age when we can sequence genomes, edit genes, and create artificial intelligence, we remain profoundly ignorant about the majority of life on Earth. This ignorance isn't just an academic concern, it's a practical limitation that constrains our ability to understand and protect the planetary systems that support all life, including our own. The deep ocean plays crucial roles in global climate regulation, carbon cycling, and nutrient distribution. The creatures that inhabit this realm aren't just strange curiosities. They're integral components of Earth's life support systems. Their loss would impoverish not just the diversity of life on our planet, but our own prospects for long-term survival. As we face an uncertain future marked by rapid environmental change and growing human impacts on natural systems, the monsters of the deep ocean offer both warnings and hope. They warn us that life, no matter how perfectly adapted, can be vulnerable to rapid environmental changes. But they also demonstrate life's extraordinary capacity for innovation, adaptation, and persistence in the face of seemingly impossible challenges. The Gulper eel reminds us that sometimes survival requires radical reinvention, the willingness to abandon conventional approaches and embrace solutions that seem impossible. The giant isopod shows us the value of perfecting a strategy and maintaining it through changing times. The Siphonophore demonstrates that cooperation and distributed intelligence can create capabilities that no individual could achieve alone. The vampire squid proves that patience and efficiency can triumph over strength and speed. The Barreleye fish shows us that new ways of seeing can open up entirely new possibilities for existence. The Yeti crab teaches us that even the most hostile environments can be transformed into opportunities for growth and abundance. These lessons resonate far beyond marine biology. In a world facing challenges from climate change to resource depletion to social inequality, the deep-sea monsters offer alternative models for organization, cooperation, and survival. They show us that life's responses to existential challenges are far more creative and varied than we typically imagine, that solutions can emerge from the most unlikely sources, and that what seems impossible today may be tomorrow's survival strategy. The story of these creatures is ultimately the story of life itself, endlessly creative, impossibly resilient, and far stranger than we dare to imagine. In their alien forms and impossible lifestyles, we see reflections of life's fundamental character, its refusal to accept limits, its capacity to transform constraints into opportunities, and its endless exploration of new ways to exist in an ever-changing universe. As we continue to explore our planet's final frontier, as we peer deeper into the abyss and encounter new forms of impossible life, we carry with us the humbling knowledge that we have only begun to understand what life can be. The monsters that shouldn't exist have taught us that our definitions of possible and impossible are far too narrow, our understanding of life's potential far too limited. In the crushing darkness of the deep ocean, where pressure would destroy us and cold would kill us, where food is scarce and light non-existent, life has not just survived, it has exploded into forms of beauty, complexity, and strangeness that exceed our wildest imaginations. These creatures are more than monsters. They are miracles, proof that in the vast canvas of existence, life will always find ways to create masterpieces in the most unlikely places. The deep ocean and its impossible inhabitants remind us that we live on a planet of wonders, a world where reality is far stranger than fiction, where evolution's creativity knows no bounds. In their alien forms and impossible lifestyles, these creatures offer us the greatest gift of all. They expand our sense of what's possible, challenge our assumptions about life and existence, and remind us that we are citizens not just of Earth, but of a universe filled with infinite possibilities for life, consciousness, and wonder. The monsters that shouldn't exist do exist. They swim and drift and hunt and reproduce in the darkness beneath our feet, living proof that life will always be more creative, more resilient, and more surprising than we can possibly imagine. In acknowledging their existence, in marveling at their impossible anatomies and alien lifestyles, we take the first step toward understanding that we inhabit a world and perhaps a universe where the truly impossible is simply what we haven't discovered yet.